Okay, I can start now. Okay, so yeah, it's a pleasure. I would have really very much liked to be there with you, but okay. In any case, I can give my talk from here. So this is some work I did. I hope you can see also the cursor moving.
Yes.
Okay, very good. So this is work I did recently in collaboration with a few people, and I would like also to remember Carlo van der Zande, who passed away last year, and he collaborated with us in this work. It's a joint work with him and other people, Henri Orlan and Takahiro Sakaue, and it's an ongoing effort, so it's continuing. Okay, so I will discuss about transition path time statistics. And what are transition path times? Okay, so imagine the simplest system that you can imagine is that of a two-level system where you have a free energy landscape like this with two minima, and stochastically a particle in one dimension that jumps back and forth, okay? And a typical situation is that of unfolding and unfolding of a biomolecule, okay? And here, if you follow the signal as a function of time, you will see typically this stochastic signal that it's going into one state, then it rapidly jumps onto the other state, it stays there for a while, and it goes back and forth, okay? So there are actually two time scales here. Actually, there are more time scales. One characteristic time is the dwell time. How long does the state, our particle, remains in one of the two wells, okay? And in the folded and the unfolded states, this has certain duration. And if you do the statistics of this duration of this, you say the dwell time, the residence time, you find typically exponential.
See the slide.
Okay, okay. So yeah, so perhaps I should accelerate a little bit so that we can reach some end. So I was saying about this two-state system and the transition paths, okay, that are this side of the, you know, this part of the transition. And here what you see, I hope you can see my cursor now. Yeah. You can see here that you know, these transition paths, they're not really a step. They have a finite duration.
We don't see your cursor. We don't see your cursor.
Okay, so I will do it without, but you can see this encircled area in zooming the signal, and then you see that, you know, the duration is finite. It's 1 microsecond in this time scale, but it's not a step. And so what I'm interested now in this talk in explaining the statistics of these very short paths, okay? So the system spends most of its time close to one of the minima, and then when it makes a jump, the jump is very rapid, but it has a finite duration, this jump. So transitions over the barriers are fast, but not instantaneous, okay? And their duration is exactly what I'm interested in. And why are we interested in this? Because in this, actually, crossing the barrier is where the most interesting physics takes place, especially in a complex macromolecule that is folding. This is where the folding takes place. Say that the molecule stays in one of the two well, and it tries to make attempts to jump over the barrier. It does some kind of contacts, but these are somehow lost time, okay? So really in the red part of the trajectory is where the folding takes place. That's why people are focusing on this, okay? So my scope of the talk is to focusing exactly on this system. So I would like to start showing a couple of experiments. There aren't so many because it's very difficult kind of measurements. But one of the system that people are studying is hairpin. I think you know hairpin. If you know DNA hairpin, I think this is a system where people studied also like Jarzynski equality and all this. But what you see in A, it's two bead kept by laser, and there is a molecule in between. This is a double-stranded DNA, but this hairpin is a piece of self-complementary part that opens and closes, and it fluctuates. And so when you measure the extension here as a function of time that you see in B, you see these black fluctuations from one side to the other, okay? And the third part, you see these transition paths. Actually, they don't have a finite, all the same duration. It's a stochastic process, okay? And therefore, each of these transition paths, when we zoom in, have a different type of duration, okay? So finally, in C, you see the histogram of this duration of this transition time. You see again, the scale is microsecond in this system, 40, 80, 120 microsecond, you read in this scale. And this is very much what I will discuss. I will discuss the nature of this distribution, okay, in my talk. Okay, this comes from, this I already said, optical tweezer. There is another system that people are studying. It's about protein folding and so on. Okay, so this is a bit of the experimental study. Okay, perhaps shall I say something about Kramer's time, or are people familiar with that?
No, yeah, please say.
Okay, so I recall that there is a classical problem in stochastic process that is of escaping from a potential well, okay, of a particle that was studied a long time ago by Kramer's. Okay, and the problem is you set a particle at the bottom of the well, and stochastically this will escape and reach another position x2 very far away from the well and then slide down. Okay. And, well, again, there are some assumptions. One-dimensional motion, the friction is high, either high or people call it moderate friction. And the barrier height, E, is the height of the barrier that the particle has to cross from the point W to the point T, is much larger than kBt, okay? This is high barrier limit. And this is the classical results of Kramer's, okay? In the high friction, the average crossing time is exponential in beta E, the barrier height. This is also known from Arrhenius, and there are some prefactors. Curvature, K and KW are the curvature. I should have used KT for the curvature at the top of the barrier. KW is the curvature at the bottom, and gamma is the friction coefficient. And there is also another result when the friction is not that high. So while the left side is the overdamped limit, the right side, you can call it moderate friction and this kind of inertial regime, okay? So this is some recapitulation of a well-known theory in this system that we are going to use, we are going to discuss and recall later, okay? Right, now we are ready to step into the problem, which is the particle in a 1D parabolic barrier, okay? So now there is, you see, in my problem, I forget about the wells that are eventually on the two sides. I'm just focusing on the crossing process, okay? So the typical setup is one-dimensional parabolic barrier, but although later I will discuss other shapes of the barrier. So the potential is minus k x squared divided by 2 with a negative sign. Of course, k is a positive. So it's a reverse potential, it's a barrier, okay? Then you have your stochastic trajectories, your particle starts at minus x naught plus epsilon, because there are two absorbing boundaries at plus and minus x naught, okay? And then you are measuring how long does it take for the particle to start at this to the left and reach the right position. Technically, there are absorbing boundaries at these two sides, okay? The other scale is the energy, k x naught squared divided by 2 is the barrier height, okay? Right, good. So people have studied this problem, and they studied overdamped dynamics, white noise, and free boundary conditions were discussed in earlier works, okay? Why do they use free boundary conditions? Actually, technically, it's quite complicated to use absorbing boundaries. So people use free boundary conditions. They let the particle recross the boundaries several times and neglect these boundary conditions. But The idea is that if the barrier is sufficiently high, these recrossings are rare, okay? So we can, and in fact, if you go to sufficiently high barrier, the two results coincide, free boundary conditions or absorbing boundaries, but they are different if the barrier is not that high. So what we are going to discuss is the effect of inertia. We are going to discuss no-Markovian power law memory kernel. We are going to discuss absorbing boundary condition. And then also we are leaving this model of parabolic barrier at the end of my talk, and I will discuss about non-parabolic asymmetric barrier and how things are changing in that case. All right? Right. Is everything clear so far, or can I go on?
Yeah, please.
Okay, so you can hear me well now?
Yeah.
And you can see well. Okay. Very good, very good. So, okay, give me some feedback once in a while. Okay, it's good. So I make some summary of some earlier works. For instance, if you look at the average, what you're asking, what is the average of a TPT, transition path time? And if you look at the literature, this is called in some paper, so the credit is given to Attila Szabo as unpublished work, so he never published that. And the first result is that the average TPT is gamma divided by k. Gamma is the friction coefficient, k is the curvature of the barrier, times log of beta e. Or you can rewrite this if you use the characteristic diffusion time. Characteristic diffusion time multiplying the log of beta e divided by beta e. And this is very surprising if you recall the Kramer's time. The higher is the barrier, the longer it takes to cross. But for transition path time, is the opposite. It's a decreasing function of the energy of the barrier height. It depends very weakly. It's not an exponential dependence, first of all. It depends very weakly, and it's also faster to cross higher barrier. And how do we understand it? This is because if we go back to the shape of the barrier, unfortunately I cannot point it, I cannot use my pointer now, but from that side, and if the barrier is very high, only a tiny fraction of the walks survive. Of course, very small fraction reaches the opposite side, crosses actually the barrier. The large majority of the walks that are absorbed and die, okay? So this is the survival of the fittest. When you increase the barrier very much, okay, you only, the very fast particle, the particle that have a special characteristic noise, they can go and reach the other side, okay? And this is how we understand this result, okay? And there is a very weak dependence on beta E that is typically not exponential, and people seem to find it back. Of course, they have not fitted the log beta E divided by beta E to their data, but what they see if they do experiments on protein folding, where the folding time, which is the dwell time actually, it's varying orders of magnitude between, say, protein A, the folding of protein A, and the folding of protein B, what they find that the transition path times are always in the range of microseconds. So even proteins that have huge differences in folding time, which means that the barrier height is different, they still have quite similar transition path times, average transition path times, okay? So this is considered as somehow supporting this Szabo formula, okay? What we will be very much interested in is in understanding and studying different cases of transition path time distributions. They were starting to my knowledge. The first paper was by Zhang and I forgot the last author of this paper. Okay, but this is the characteristic shape of a transition path time distribution. So this is a histogram of transition paths, and in the horizontal is 2 times d times t, so in dimensionless units. And you see that there are very, very short paths of very short duration, then you have a maximum, and then you have a decay, okay? So I will study this in different situations, okay? And okay, so you see that here they're plotting simulations and equation 49. Equation 49 is some theory that I will discuss. And there is a small difference between the two, and the difference is exactly due to the boundary conditions used. For that theory, equation 49 uses 3 boundary conditions, okay? And this difference decreases as you increase the size, the height of the barrier, okay? All right, so I'm now reporting about the work we did in 2017 with Henri Orlan, and it was our my first work in these transition path times. And with Henri, we thought, okay, why don't we study the effect of inertia in this problem? So we know that in a typical biomolecular system, the system we have in mind that we model in statistical mechanics, typically are overdamped, so you can neglect masses and inertia. But we thought, okay, but these transition path times are very short, and why don't we study this problem? And that's what we did. We derived the transition path time distribution. Actually, we found a nice universal form of this transition path time. So you see, we write this transition path time distribution as a function of some function g, which turns out this shape is quite universal in the sense that if you have a different process, what it changes the G. And and the G is given by the deterministic solution, x naught of t, of your process, which is a sliding function. Okay, the deterministic solution doesn't cross the barrier because if you start from the left, it slides down, but it's still in there. And the variance of the process, it's Gaussian processes, and it's like that, okay? In this universal form, we can rewrite and find the G that corresponds to the overdamped limit, which was already found. And if you work out the asymptotic of this at short time, at a long time, you find that at short time, t equal to 0, it has an essential singularity, okay? This is rapidly going to 0. So the t going to 0 limit is exp of something, some characteristic time, the diffusion, divided by t. In the short time, there is no barrier height dependence, okay? There is nothing like k and so on, because it's just the very fast particles that find the very favorable noise such that they can cross this barrier, okay? The t going to 0 limit is the limit that you see in this distribution. It's going very rapidly to 0 exponentially on the left side of the graph. Okay, let's back to this slide. On the right side of the graph, when this exponential decays as omega is a characteristic ratio, there it enters, of course, the barrier, the k, the curvature of the barrier, okay? And now we have our results, and we have these results. So you see that what is the effect of inertia here? It's only at very short times that we see an effect. And in this going to 0, at time t going to 0, there is instead of, not surprisingly, instead of a t, there is a t squared, 1 over t squared. But at long time, you have the same statistics and so on, okay? All right, so actually we see that, again, this effect of inertia, it's a very, very short time, unexpected, well, perhaps not very surprisingly, but okay, we have derived the full exact distribution in this case, and perhaps in some situations can be used this, okay? Right, so this was our first work. Actually, we found out that this actually could be easily generalized to generalized Langevin equation, okay? You know that the generalized Langevin equation describes more complex processes where one has memory, and this k of alpha, this calligraphic k of alpha, it's a memory kernel, okay? If you put a delta function, you go back to the ordinary Langevin equation, but we use here, instead of power law, correlated power law memory, because this is the strongest one can have, and it's also justified in some classes of polymer physics problem. Okay, this alpha, it's a power that is going between 0 and 1. And of course, there is a relation between this kernel and, when alpha goes to 1, how we define this kernel, how we define this A of alpha, is such that when alpha goes to 1, you recover the normal Markovian process. Okay, so the further away is from 1, this alpha, the smaller it is, the stronger is the memory effect. Okay, and the TPT distribution also for this process has this universal form, but now what we find is that this G squared, instead of being, where we are studying here, of course, you see this is the first order, so we don't consider here inertia, but we consider this memory, and we find a modified form of G squared, which contains, instead of containing exponential, contains what is called the Mittag-Leffler functions, which are modified exponential, okay? And when we analyze the asymptotic of this, we find that when t goes to 0, we find an exponential of t naught characteristic time divided by t to the power alpha. So here is where in the left part of the distribution where we see the effect of the memory, okay? Whereas for long times, it decays exponentially, okay? And this is a bit it could be surprising because the memory kernel is a power law decay, so you would expect, it influences all time scales, but there is the time scale set by the shape of the barrier that dominates, okay? It is an exponential, and we are disagreeing with some previous results, okay? In the group of Makarov, there was a work predicting stressed exponential decay, which we don't see, and I think it's, they're using a kind of different approach. We have also some arguments explain why it's exponential and not stretched exponential. Why actually the effect of this memory kernel is going away for long times, okay? And, so it's the idea is that that the effect of the barrier or the effect of this potential is destroying this memory, the effect of the memory kernel. Okay, there is an argument, and the paper is mentioned below. All right. So now the next thing is that we were interested in working with actually absorbing boundary conditions. Because all this and all the previous work, we are neglecting that actually our path starts from left and goes to the right, but it should never cross the two boundaries, okay? Technically, how you measure and how you define a transition path is that the particle should not cross the two boundaries, okay? So how to impose the absorbing boundary conditions in this case? So, of course, we start now from the Fokker-Planck equation, and where this is given here. This V of x is our potential barrier that in this first work was a parabolic potential, this V of x, but later we generalized to other type of potential, okay? So the right-hand side, we write LFP, so it's the Fokker-Planck operator acting on P of x, which is the probability, okay? And it's the first, so this is an equation. So we use absorbing boundary conditions. We want to enforce that the probability at the two ends is 0, okay? We want to enforce this. All right, now we have a technical problem. It's not, it's well known that, the Fokker-Planck operator is not non-Hermitian, okay? So it's not suitable to do some spectral decomposition because you would like to work with eigenfunctions or something that are orthogonal with each other. So to use this, and to do that, we you take a book of Risken, and this is how I explain to do it. Instead of working with the P of x, first of all, we separate the variable. We have an exponential decay contribution in time, where lambda, and then instead of working with just a function of x, we use this decomposition x of minus beta vx divided by 2 times qx. All right? So our function is now qx, right? And for qx, we obtain a Schrodinger equation And this is exactly what the transformation does. So this Schrodinger equation now is Hermitian. Actually, we got rid of first derivatives. The first derivatives are the term that gives non-Hermitianity, okay? But we get now an effective Schrodinger equation, and now the boundary conditions are on Q. But this Schrodinger equation, the Schrodinger operator is Hermitian now. Therefore, we can work with orthogonal wave functions, the equivalent of wave functions, okay? And now, what is V effective? The effective is what you find when you do this transformation. It's related to the original potential. So our original potential V of X was a parabolic barrier. Now I use the small letter K here to indicate the curvature of the barrier. Unfortunately, in my previous slides, there was a capital K. It's the same variable K. It's defining the curvature of the barrier. And so you see, when you have a V of X parabolic, this transformation gives you, again, a parabolic function. Okay, this is well known, and so on, and this is how you solve your problem. Okay, it's again a parabolic function, and this effective potential depends on the temperature, of course, because it comes from this transformation. And what is very interesting, and perhaps so even if we start from a V that is a negative, that is a barrier, has a negative curvature, you see that once you do this transformation, you always get a positive curvature in V effective, right? Because it depends on K squared. So it's irrespective on the sign of K on the curvature, you get always a positive V effective potential. So the effective potential has positive curvature. All right. Okay, so this is the transformations that we are using, and we are going further, and we are working with this Schrodinger-like equation. All right, and now we have to find the solutions, and the solutions are hypergeometric functions. Of course, this is the harmonic oscillator, right, of quantum mechanics, but it's different. We want to enforce absorbing boundary conditions. Therefore, our wave function has to vanish at the interval, all right? So we are here changing this S of n, which is related to the lambda, until we find the zeros exactly at the right point, okay? Like quantum mechanics, we have even and odd functions. So the red is the lowest, the ground state. So you see the top figure shows the ground state is in harmonic oscillator, infinite domain harmonic oscillator. This would just be an exponential, right? But we are enforcing it to be zero at the boundary. So it's almost, a Gaussian. So almost a Gaussian, but it's going to zero at the boundaries. And the odd, the same, they're all enforced to go to zero. Okay, so the spectrum is this S of n, that we have to tune this S of n such that we have the zeros at the right point, and we find numerically the spectrum. Okay, so the similar to quantum harmonic oscillator, but the wave function vanish at finite boundaries, at the boundaries, okay, not at infinite, okay. Normally, how to find the spectrum of harmonic oscillator in an infinite domain, you require that this F1, it's a finite polynomial, then you get Hermite polynomial, and this S of n is an integer, okay. That's how you find it in ordinary quantum mechanics, but here we impose finite zeros, okay? So, and it's also quite important for what I'm going to say later, that we enforce this boundary condition. So the low-lying excited states actually, like, they're almost like harmonic oscillator. So the spectrum scales like in the ordinary infinite harmonic oscillator, where the energy is growing with the quantum number n. But the highly excited states, they scale as n squared, because this is like when you go to high excited states, is like you have a particle in a box, right? When you go up and up in energy is, what makes the quantization is the boundary. The system doesn't see anymore the potential landscape below. And this is important for what I'm going to say later, that you have these states. Okay, now we have this obtained the spectrum, and we start from our solution. We want to be an initial condition, a delta function in the source at minus x naught plus epsilon, and this is how it looks like. And here we have a spectral decomposition. We can only write this because the Q of n are orthogonal to each other. And so this is how you do, well, in quantum mechanics and so on. And then, for every Q of n evolves with the corresponding eigenvalue. This is lambda of n, okay? So this is the shape of the P of x, the exact shape of the P of x, if you start with the delta function on the left side of the barrier, okay? All right, so this is I recall this is our barrier. So what we do, we put a delta source here, and this is the previous expression, and we calculate the TPT distribution. The TPT distribution is the current going through x naught, okay? There is a finite current of particles escaping from this other boundary, and this gives the TPT distribution. So you know the current is related to the derivative of the P, and then finally we find this nice symmetric expression for the TPT distribution. It's a sum of eigenfunctions, so that there is the derivative of the Q's at x naught and at minus x naught, okay, and with a decaying exponential, okay. So this is a series of infinite terms, but the terms have alternating signs, okay. The Q of n are the wave function at the two sides, and you realize easily that this product has opposing sign, because I can go back to the previous slide, okay. So if you look at the red curve on the top, the derivatives at the two edges, they have opposing sign, okay? One is positive and one is negative. When you go to the n, that's the n equals 0. When you go to n equal 1, you have one node, okay? Unfortunately, I cannot use the cursor here. If you go to the red curve below, okay, in the odd sector, you have one node there, therefore the signs of the derivatives swap, okay? And so on. So for every n even in the even sector, the derivatives at the two edges have the opposing sign, and on the odd sector have the same sign, okay? So which makes that this transition part time, the spectral decomposition, is a series with alternating signs, okay? Because of these derivatives, okay? And now we can find it, and we found, okay, what's the TPT distribution. So what we have to find numerically the lambda of n and find the Q of n, these hypergeometric functions that put them together, we sum 100 of them, okay, and we find this distribution, okay. Of course, it's not a full analytical function as for the free boundary conditions, but we have to do it this process numerically, but it's not very efficiently.
Hello?
Okay,
Question?
so yeah.
Where did the epsilon go? Are you computing over is it a conditional probability?
Yeah, it's always a conditional probability, yeah.
So you are dividing by normalization, and that...
Yeah, I'm normalizing by A to have it...
The formula in the previous slide, if you take the epsilon going to 0, I thought it will go to 0.
If you take what? Sorry?
Epsilon going to 0, this Qn, doesn't it go to 0 if you take epsilon go to 0?
Yeah, but that's true. That's why you have to do the Taylor expansion.
Yeah, but then it has a term proportional to epsilon at least.
Yeah, but you have to divide. Of course, in this limiting case, it's a bit delicate. It's explained in the paper. You have to divide by this shows, as you are correct, if you start epsilon going to 0, you know, and so everything is absorbed, okay? So you have a finite number of
conditional over the paths that are surviving.
Yeah, exactly. You have to do it, it's a bit delicate. You have to do exactly as you said. Yeah. So, and that's why this, when you take the limit in this previous expression of epsilon going to 0 in Q of n, then the first term is 0, but then you get Taylor expansion, and you get the first derivative in minus x naught. Okay? You get the first derivative in minus x naught. That's what you see here, okay? And this is our results. Solid lines are absorbing boundary conditions, and dashed line are free boundary conditions. If the barrier is very high and you go to the k is equal to 16, then you find overlapping distribution. But for, say, moderate k, already k equal to 4, now I don't remember if k equal to 4 is exactly 4 times kBt or 2 times kBt. I have this doubt, but you see, if you look at the blue line, you see there is quite some difference between the two distributions, okay? So what we are saying is that we, why not imposing the boundary, free boundary conditions for experimentalists is a bit more cumbersome because they have, but we have a website that fits this empirical distribution. Actually, I'm a bit embarrassed because I'm not sure that this website is still up, okay? But it, this last web address gives you a server where you put experimental data and you get out the fit with absorbing boundary conditions. But I have to check, and perhaps this is something we did 2 years ago, and it needs to be updated. But okay, so we are using this imposing absorbing boundary conditions. Perhaps a bit more interesting is, and now I'm moving to the last 2-3 slides. We are going to study asymmetric potentials, because what we were curious about is that, okay, everybody studies this parabolic potential, but what is the effect of potential shape on the transition path-time distribution? Okay, and so what we are studying here is a class of potentials. We decided to use this type of potential, and you see the red, the blue, and the green, they are increasingly asymmetric. Okay, so we introduce a parameter B, which is the position of the joining point of two types of potential. On the left side, we have a piece of parabola, which continues with a straight line, such that the derivative is the same. Okay, so you see that this black dot shifts, and the position of the black dot is equal to x naught divided by 2, 1/2 for the red, 0, and then minus 1/2 for the green, okay? So this is shifting, and so a fixed endpoint distance, okay, and fixed barrier height. So we are changing the shape of this potential. Of course, we want to keep the endpoint fixed, and we want to keep the height fixed, okay? So, and we want to study this effect. And now if you do the effective potential, the equivalent quantum mechanical potential for this problem, you're solving your Schrodinger equation in the potential which is shown on the right side. Okay, so the effective potential, the formula for the effective potential is shown again here at the bottom. So it contains second derivative and first derivative of the original potential. If your potential is linear, if v of x is linear, then you see that this just gives you a constant on v effective. And this is exactly what we see on the right-hand side. On the left-hand side, on the left part, we have, on the right or right-hand side of the right figure, okay? Again, I cannot point it, unfortunately. Right, so you see this flat. This is constant, okay, and it has a parabolic part on the other side. So you see this potential, this v effective has a parabolic part, and it has a jump on here. So it's a potential. It's a quantum mechanical problem of this type. But we know in textbooks they are you have a finite jump in the potential, so what you can solve it, you can find the eigenfunctions and so on and so on and so forth. Okay, we are still using again boundary conditions, absorbing boundary conditions at the two edges for this type of potential. Okay, right, and so for again the colors codes are the same. We are going to increase asymmetry. Okay, and that's what we find. These are our transition path-time distributions. Okay, so just the first line shows one thing. There are two relevant parameters in our transition path-time distribution. One is the diffusion coefficient, and the other one is the barrier height. Unfortunately, in this part of the slide, again, I changed a bit notation. In the previous, I had gamma for the friction coefficient. Here I use D. Diffusion coefficient, barrier height is indicated with delta U. Okay, there are these two parameters. So what we find is that actually we don't see any sign of the potential shape, in the sense that given a transition path time distribution generated from asymmetric potential, we can always fit it with a parabolic potential. And actually what you see here on the main part of the figure, there are two curves on top of each other. One is a dashed line, and the other one is a solid red line. The dashed line is a blue. Okay, you see they're perfectly on top of each other. One is generated from an asymmetric potential, and the other one is that it's a fitted result from a parabolic potential. Okay, so actually we cannot distinguish the potential shape in this figure, and the inset shows how we calculate this transition path time distribution by summing eigenfunctions. You see how the convergence of the series is going. Okay, so you see if you take only one element of this infinite series n equal to 1, you have an exponential decay, and this is the black figure indicated with first. If you take two terms, you have the dashed line. Okay, the exponential decay, of course, does not capture this turnover of this red curve. Okay, it's only going exponentially, and it goes to a maximum at 0, and the next term and the third term. So this inset shows that actually you need only 5 or 6, perhaps, of these terms to capture the whole transition path time distribution. Okay. And this is a bit of summary of actually the message that we want to convey in this story, is that actually you always, this transition path time distribution, this TPT, is very robust and universal, in the sense that if you generate from one arbitrary potential, right, you can always fit it to a parabolic potential. And this is what the figure shows, right? The bottom figure shows on the left the potential V of x. Okay, we start with the green and we make it, so the green has a certain barrier height is equal to delta U is equal to 4. Okay, the red is a parabolic linear potential with an asymmetry, strong asymmetry. Okay. And the dashed one is again a parabolic potential, but with half of the barrier height. So you see the barrier height is 2 in these units. Okay. So what you see on this, on the right graph, is the transition path time distribution for these 3 cases. Okay. So you see that red and dashed blue, they actually almost overlap in distribution. Actually, we could have made it overlap if we had tuned a little bit more the delta U on the dashed one. Instead of taking perhaps 2, we could have taken 2 point something. We would have made it overlap. Okay, so the message is that it's your asymmetric. You don't see, these data do not resolve the potential shape. You don't see much trace of the potential shape. Even if you go to a very asymmetric potential, you can always fit your data with a symmetric potential, but you have to be very careful, because the parameter that your analysis spits out, gives you, are not the original parameters. Okay, so if you were to fit the red curve data with the parabolic potential, you would say your barrier height is equal to 2, whereas your barrier height in the red curve is 4. Okay, so this leads to very wrong estimates, especially for delta U. Okay, and I remember the first line of this slide shows that there are 2 relevant parameters, the D diffusion coefficient and delta U barrier height. Okay. So what we find is that the delta U, if you do this exercise, and this is what we do here, okay, we fit asymmetric potential. So we take an asymmetric potential, we generate a transition path time distribution, and we insist of fitting this to parabolic barriers, okay, data. And we are asking what is the output of this parabolic barrier. So I have two outputs as parameters. I have the barrier height and I have the diffusion coefficient, okay? So if you look at this table, the top gives you the beta delta U 4 and the D 2.5. These are fixed, okay? And then there is a B coefficient. The B tells me the increasing asymmetry of my potential, okay? So this is the B is the same parameter that I have in this curve here, that it's, B is the position of the circle in this potential graph, okay? So when B is equal to 1, you have actually a perfect parabola. When B is going towards -1, you have the strongest asymmetry. You have like a sawtooth profile, okay? So in this last table, you are increasing the asymmetry going from B to 1 to 0.5 to 0, minus 0.5, but your parameters, beta delta U, the height is 4 and D is 2.5, okay? And now we fit these shapes of transition path time distribution to a parabolic case. Of course, in the case B equal to 1, we find back delta U equal to 4 and D equal to 2.5, because B equal to 1 is a parabolic potential. But when we increase the asymmetry, you see that this beta delta U the estimate, it's very, very varying, okay? And if your asymmetry is strong enough, you get a factor that is larger than 2 sometimes. And whereas D remains quite constant. The variation in D and the diffusion coefficients are much smaller, okay? The same for another type of barrier. Here, the effect is dramatic, even more dramatic. When we increase the asymmetry, we were tempted to say, okay, our result would give us a barrier of height 0.3, okay? Whereas delta U, the real delta U is equal to 4, okay? So fitting, it's always an excellent fit of quality. That is the parameter chi gives you an absolute value of the fit, but the delta U is very, very bad. And this is very interesting because this is exactly what it resembles, what people find in experiments. Okay, I just end quoting a review, quoting a quote from this review by Hofer and Woodside. Okay, so there is one particularly interesting disagreement, is that the energy barriers implied by fitting transition path time distribution to the theory are very small, much smaller than the barriers found from kinetic and thermodynamic analysis. And I think that our work points to one potential problem with this fitting is that to do the fitting and to extract realistic values and the right values of these coefficients is one has to know the shape of the barrier. Okay, so otherwise you would find something much smaller. And actually, we were very pleased to find a factor 10 of difference. So if you look at the table on the right side, you see that beta delta U on the fit goes from 4, 3.5, 0.3, okay, in this Morse-like barrier. This is one order of magnitude. You were inclined to say, okay, your delta U is one order of magnitude in what it actually is. And this is exactly what they find in experiment. They find one order of magnitude difference, okay. Right, so this is the end. I'm here at the conclusion. So what we studied is this transition path time distribution. This is a shape that we see here. We have discussed it for several models. This is something people are very interested in. Experimentalists try to measure these transition path times for several systems because they tell you what happens actually at the top of the barrier where most interesting things happen, okay? Single molecules technique were used to characterize transition path times. And what we showed actually here, that many features of the transition path time distribution are universal. Actually, this transition path time distribution, as I said, it's very much independent on the underlying dynamics. When we studied, for instance, we study non-Markovian effect or colored noise and so on, we see that this modifies this distribution only at the beginning at very short times, but there the statistics where these probability are going to zero, and actually they are not really measurable. Even when you put noise with this power law kernel, okay, you see that it's still exponential at long time. Okay, so there are many universal features of the underlying dynamics, but of course, when you measure one distribution and you find some try to fit your the parameters that you get out of it, one has to be very careful, because the parameters that are coming out, they are very sensitive on the potential shape. Okay, so although the distribution is universal, one has to be careful in this case. Of course, knowing the potential, the underlying potential, is very important. Okay, and the final question is that are 1D models eventually with memory suitable to describe this folding dynamics? And actually, I end my talk here. Just if you're interested, there is an excellent review. Actually, it's very short, just a few pages, by Hofer and Woodside. And Woodside is the leading experimentalist measuring these transition path times. And I think the review is very nice. It shows the experiments on one side and the theory and the open issues and so on. Okay. With that, I thank you for your attention. Thank you very much.
Hi, sir. So you argued that you cannot be sure of the model parameters because there is a degeneracy in the plot. So is there a independent way to find out the potential landscape? Like say looking at the duty cycle of the signals or something like that, not looking at the transition path probability also.
Yeah, there is. If you use the Boltzmann inversion, for instance, if you have a reaction coordinate, sorry. So now perhaps you can see my cursor. Do you see the slide?
Yeah, we can see the slide.
Okay, so if you look at the statistics of this signal, right? And you can plot an histogram in time. So you record it in time, you can plot it an histogram. Of course, your histogram will be picked around the two minima, okay? But by the occupation of this reaction coordinate, you can plot actually an energy landscape. But often is, because of this transition region is very short, it's not very detailed. What you, I don't know if it's always reliable, especially in the transition region. What is okay? So this free energy landscape, I can map it from the signal as a function of time, right? Do you understand? And then if I do a good job, I would have a good statistics in between. I would have a nice landscape in this transition region. You see that what you see in this transition region is not a perfect parabola. Does it answer your question?
Yeah, but I think I'll have to look at.
I cannot hear you. I can't hear you.
Yeah, somewhat, but I think I'll have to give it a look and then try to figure out. But thanks.
Okay. Yeah, you're welcome.
A question. I have two questions.
Yeah.
Yeah. So these transition path times, are they how different are they from the residence time? If I look at the amount of time that the particle spends over this region, the transient region, and if I compute that amount of time the particle spends in that overall in an experiment, and do a statistics on that, will that statistics be different from this transient path time statistics? This is one question.
I don't. Are you talking? What are you calling about the residence time? Sorry.
The amount of time the particle spins. Let's say you are observing the particle over, let's say some amount of time. Let's say capital T. And out of that capital T, some fraction of time it spins over this transient region.
Yeah.
Is it exactly the same time, the transient path time?
I'm sure. I don't think I understand your questions exactly. So you are in the transition region.
Yeah. So he's
so
asking.
the time that the particle spends in the transition region.
So see in your picture on the slide you're showing the leftmost picture, there's double L potential picture. So there is in the middle there is a shaded region, right?
Yeah.
So I suppose I observe the trajectory of the particle and compute the amount of time the particle spends in that shaded region. So I can do that. Suppose I observe the particle for an hour, and in that hour-long observation, I can find out the amount of time the particle spends in that shaded region. Now I get a number. Is that number same as, can I call it as a TPT?
And well, I think you will be measuring many of these transition events, because in this half an hour, the particle would have stayed in the red region, but then it will go to defold it, and then back in the red. And if you are blinking, so if you're counting, you're integrating many transition paths times in that case.
Yes, so fraction of time it spends is basically the average of that will be same as the average of TPT, right?
Yeah, well, you're counting many events of transition paths, many transition events. So therefore, you will have to divide by how many to find the transition path. The transition path is one event.
Okay, so that would be basically sum of many transient events.
Yes, exactly. Yeah.
The statistics will be the sum of those. Yeah, so the statistics may be different.
Yeah.
And the second question, you said that if you have very large barrier, then your TPT is it decreases with increasing energy, increasing the barrier height. Can this be understood by this optimal fluctuation theory, which is basically looking at the path, optimal path, which actually takes you from left-hand side to the right-hand side, and find out the amount of time in such a path if the particle spins in that region?
I don't know this theory, but do you understand my argument? Do you understand my argument?
Yes. So what I'm... yeah, please tell.
Yeah, so my argument, so perhaps I will stop sharing and I can... Do you see my... Do you see my blackboard?
Yeah. Yes.
Okay, so we have a barrier, right? Okay, so if I would have no barrier at all, right? A flat landscape, and I start from here. Okay, do you see? So my transition path time, I can still define it. Okay, many times the walk will be absorbed. There will be a few walks that are arriving here, okay? And then I can measure the average transition path time. All right? If I now have a small landscape, I will still have a fraction of walk that they make it to the other side, okay? When I go to an extreme high barrier, okay, let's say an overwhelming majority will be absorbed to make it to the other side, they really have to have a fast and very, very favorable noise that makes them going through, okay? So they must be very, very fast, okay? So it's a conditional probability on the fact that they can cross, right? So when you count the number of events, you know, when you measure this average of transition path times, it's average on the number that are crossing into the other side. This number is extremely small, and they have to be extremely fast to make it. And that's why, on average, this transition time decreases with the barrier height.
Yes.
Does it...
Yeah, I understood. But my question was, a path, you can actually probably find out the path by which in an optimal fluctuation can actually take the particle and cross that high barrier, because this is a very rare event. and you need a very optimal fluctuation, and such optimal fluctuation would give you a path, and that path, if you compute that the time spent in that path in that region, probably it will also give you this explanation of 1 over E.
I think probably yes. There is another way to derive this you're saying, and yeah, I think so. Yeah.
Okay, thank you.
You're welcome.
Thank you, Enrico. Yeah, there is one more.
Hi, Enrico. And I still bother you with some confusions I have. So again, it is related to the two previous questions. So the first question was somehow to get information about the potential, right? And you were also emphasizing it is important for experimentalists that they all know what the shape is of that potential. But then somehow I didn't understand another remark that you made, namely the universality. Somehow these two seem to be in contradiction. Because if it is universal, for many different, you were even mentioning there is molecule A and molecule B, and they have the same transition path on average. So these seem to me remarks which are contradicting each other, or maybe I misunderstood.
So that remark, I made it in another context. That remark so there were two different kind of things that I said. Okay, one I said about the average TPP. Can you see this?
Yes.
Okay, the fact of going as log beta E divided by beta E versus the Kramer's time going as x of beta E. Okay. So I said, let's say that you have two proteins like A and B, and let's say that the barrier of the first A is around 2 kBt, and the other is 4 kBt. Okay. So the difference in their Kramer's time is large, right?
Mm-hmm. Yes.
The difference in their TPT is small. It's just a factor 2.
Yes, I understand.
But the other one, it goes into the exponential. Therefore, I said, when people measure and take two proteins and they measure enormous, very large difference in their Kramer's time, in their residence time, they still measure very similar TPT.
Yes, but that's why I was asking, why is it then interesting to the extreme? Because it seems that you can have very different heights, you maybe have different shapes, and you always have the same universal distribution. So I don't understand how to combine that with your remark that experimentalists are so interested in it to understand the shape.
The shape of...
Maybe I misunderstood, but you say they are interested...
So the experimentalists measure something, okay, and in their transition region, and they're very much interested, do I see something that makes sense?
Uh-huh.
Okay, because the time is one thing, but then finally they want to, well, suppose that your folding is not a a two-state model, but there is more complicated.
I see.
So do you see something more complex than this 1D barrier crossing or not? This is the question they have.
I see, okay.
So they want to understand whether what they measure, okay, makes sense and it's consistent with other measurements. Like they can measure the barrier height from Kramer's, okay, and the first thing that they ask themselves is that is consistent or what I see with when I measure transition path time. Do I see the same height, barrier height?
Yes, okay.
And their conclusion was there is a factor 10 of difference, and that's what I said in the last slide. Okay.
Okay.
What we are saying is that this number you have to extract, you have to make sure that you know, in transition path times, you have to make sure that you know the landscape to extract this barrier height reliably.
Okay.
That's what we...
Okay. And then a second confusion that I had was that you are speaking about Kramer's theory in terms of residence times, no dwelling times. But there is another version of it which is called reaction rate theory, and they give the reaction rate. You know, they make they make a Markov process which is now two-state, the fold and the unfold, and that means that there is an exponential waiting time to go from the fold to the unfold. But it seems that what you are saying that it is not exponential, because it's the sum of two distributions, one which is exponential and one which is related to the transition time distribution.
No, in this theory, when you talk about rates directly, of course, you don't even look at the transition path times. You don't have a resolution to get into that.
If you measure suppose you are a molecule in the folded state, and you wait and you see when is it unfolded, so you won't. This will not be exponential. So there is.
I would say.
I mean, how can I understand it? Because there is a transition time in between.
Yeah, but this transition time is typically order of magnitude smaller than the dwell time. Therefore, people in that description, they ignore the transition time.
Okay. So, but in Kramer's reaction rate theory, this was somehow, or it is somehow ignored or neglected because there is a particular scale. I don't remember the scale where this transition is neglected, but it must be somehow, I guess. Okay, I give back to Anupam.
Okay.
Okay, thank you, Enrico. Thanks very much.
Oh, you're welcome. I hope it was clear, but okay. I can send the slides if people are interested. Just let me know. And they can always contact me if they have a question.